My name is Linda Young, and this is my presentation for Lab 3. The purpose of this lab was to analyze a star's motion around a black hole and estimate the mass of that black hole. We will essentially work backwards and use the object's motion and key physics principles to find the forces acting on the object so that we can then find the mass of the black hole. The applied physics principles for this lab are Newton's second law, which will help explain the interactions between the system and its surroundings. Using Newton's second law, the net force can be calculated as the change in momentum divided by the change in time. To derive that, I use F net equals ma. Acceleration is the same as denoting the change in velocity over the change in time, and the change in velocity times the mass is just the change in momentum over time. F net can be further broken down as the sum of the parallel component and the perpendicular component. The parallel component represents a change in the magnitude of the momentum, and the perpendicular component represents a change in the direction of the momentum. Newton's law of universal gravitation states that every object attracts every other object in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This is the formula for the gravitational force, and the formula below shows F-grav in vector form, and to do that we simply multiply by negative r hat. We will later rearrange this formula to solve for the mass of the black hole. There were a few assumptions that we needed to make. The mass of the star was given as 2 times 10 to the 30th kilograms. The net force on the star is due solely to a black hole, which we were also told was located at the origin. Lastly, delta t is the time between data points in our trajectory, which was given as 1 day, which is equivalent to 86,400 seconds. One of the first things I needed to change in my code was align with the variable seed. We needed to make this change so that we could generate a trajectory unique to our GT emails. Since we will be using the gravitational force formula, the gravitational constant used is 6.67 times 10 to the negative 11th. Again, the star's mass was given as 2 times 10 to the 30th kilograms, and we converted 1 day into 86,400 seconds for delta t. The star's initial and final velocities were given in the code. The initial and final velocity was used to calculate the initial and final momentum by multiplying m times v. So for the initial momentum, that would be the star's mass times the initial velocity, and for the final momentum, that would be the mass times the final velocity. The star's change in velocity is denoted as v final minus v initial, and the change in momentum is denoted as p final minus p initial. The rate of change of the momentum was found by dividing the change in momentum, which is the change in velocity, by the change in time, so delta p over delta t. F net is just another way of denoting the rate of change in momentum. F net parallel was calculated by finding p hat, which is the unit vector for momentum. We solved for p hat using the initial momentum divided by the magnitude of that vector. To find the parallel component, we need to find the change in magnitude of the momentum over the change in time, and then multiply that by our p hat vector. To find F net perpendicular is quite easy since we already have the parallel component. Knowing that F net is the sum of the parallel and perpendicular components, we can just subtract the parallel component from F net to get F net perpendicular. Finally, to calculate the mass of the black hole, we need to find the distance between the black hole, which is located at the origin, and the star's position, and this is shown by the variable r. The gravitational force equation can then be rearranged to solve for the mass of the black hole as shown in the code and in the picture to the right. Here is my glow script model of the star's motion around the black hole. The orange arrow is F net vector, which indicates the sum of all the forces. The blue arrow represents F net parallel, which represents the change in the magnitude of the momentum, or in other words, indicates slowing down or speeding up. The pink arrow is F net perpendicular, which represents the change in the direction of the momentum, and that always points towards the kissing circle. Using the code, the mass of the black hole was calculated by using the average of all the other values, and the estimated mass of the black hole was about 7.2 times 10 to the 33 kilograms. According to Newton's second law, the change in momentum over the change in time is directly proportional to the net force, so the two are equal to each other but only numerically. It is important to note that F net is the sum of all forces acting on the system, which causes changes in the object's momentum and overall motion. And in contrast, the rate of change of momentum specifically explains the changes in speed and direction of the object. The two are calculated differently. For F net, we have to use Newton's gravitational formula, and for dp dt, we have to use a change in velocity. The answer to question 2 is no, because we're using the same conditions, which is that the new black hole is placed in the same location as the previous one, and that the star's motion is unchanged and is only affected by the gravitational force of the new black hole. Therefore, it is not possible to find a value for the mass of a new black hole that is different, because there would need to be a change in motion to determine a new net force. Sources of error include the assumptions made. We assumed that the only surroundings interacting with the system was a black hole, and in observing the computation model, we see that the star's direction and overall motion is changing. This is caused by changes in the F net parallel and perpendicular vectors, and therefore net force will also change, which is why there are fluctuations in the mass of the black hole. As a result, our model is not as accurate as it could be. Overall, by rearranging Newton's second law and the universal law of gravitation, we can find the unknown mass by looking at the trajectory of an object as well as its interactions with the surroundings.